Hello friends, in this video I am going to show you the use of Zener Diode as a regulator. But before starting the video, I request you all to please subscribe my channel. Zener diodes are special type of diodes which can be used in the breakdown region. But by using its quality, Zener diodes can be used as a regulator. That means it can keep the voltage constant, and a regulator is the device that can keep the voltage constant. Zener diodes can be used as a regulator in three processes. That is, if we keep the input voltage Vi and the load resistance RL both fixed, we can use it as a regulator. And next, if we keep Vi fixed and RL variable, we can also use it as a regulator. And by keeping Vi variable and RL fixed, we can use it as a regulator. So before starting the Zener diode as a regulator, we have to know that whether the Zener diode is on or off. So for this we need to use the Thevenin's theorem. We have to determine whether the Zener diode is on or on. So from this we can see that if we apply Thevenin's theorem here, then the Zener diode Vz will be open circuited. Then the load voltage, that is V is equal to VL, will be RL into Vi, that is input voltage, by RL load resistance plus R. So if V is greater than Vz, that is the voltage is greater than Zener voltage, then the Zener diode will be on. But if V is less than Vz, the Zener diode will be off. We can easily understand it if we solve the following math problems. So in this problem, we have to determine the load voltage, the current IR, the current IZ, that is through the Zener diode, and the power PZ. And for this, here it is given that RL, the load resistance, is 1.2 kilo ohm, the input voltage Vi is 16 volt, the R is 1 kilo ohm, Vz is equal to 10 volt, and Pz is equal to 30 milliwatt. So at first we can find the VL. Here VL will be Vi into RL by R plus RL, that is the previous equation. And if we put the values, then VL will be 16 into 1.2 kilo ohm by 1.2 plus 1, that is 8.73 volt. And 8.73 is less than 10 volt, that is less than the Zener voltage. So we can say that the Zener diode is in off state. That means no current flows through it. So Iz will be 0, and as Iz is 0, the power P, that is equal to Vz cross Iz, is equal to 0. So the no current will pass through the Zener diode and the power will also be 0. Then if we want to determine the VR, by applying KVL, we can find VR is equal to Vi minus VL, that is 16 minus 8.73, that is 7.27 volt. And IR is equal to VR by R, that is 7.27 volt by 1 kilo ohm is equal to 7.27 milliampere. And by this we can determine the IR, load voltage VL, Iz and PZ. So this is it. And if we apply R is equal to 3 kilo ohm in this circuit, then what will happen? We can see for RL is equal to 3 kilo ohm, and if we put the values, VL is equal to 16 into 3, that is 16 is the input voltage and 3 is the load resistance by R plus 1. So VL is equal to 12 volt, that is it is greater than 10 volt, that is it is greater than the Zener voltage. So it is on, the Zener is on. Now VR, so the VR will be Vi minus Vz, and we can see it from the KVL. VI is equal to VI minus VZ is equal to 16 minus 10 volt, that is 6 volt, and IL, in this case IL will be VL by R, that is 3.3 milliampere. And as there is current, as the Zener diode is on, so there will be current through the Zener diode and it will be IZ. And if we apply KCL, we can see that the current IR is entering this point and IZ and IL are leaving. So if we apply KCL, we can solve IZ is equal to 6 minus 3.3 milliampere is equal to 2.67 milliampere. So by this we can also identify PZ, that is VZ into IZ, and PZ will be 26.7 milliwatt. So we have finished this. So by this we can say that we can identify the VI and RL through this. And if the VI and RL both are fixed, we can say that what will be the current and voltage through this Zener diode. Next we move the region where VI is fixed by RL is equal to variable. RL is variable. That means in this case we have to determine the RL, and the Zener will be on and off because of this RL, and it has a maximum or minimum value for which the Zener will be on. So RL will be on only then when IL is RL will be actually minimum when IL is maximum, because R is equal to V by I, they are inversely proportional. So RL, so we have to determine the IL and RL. Let's move. We know that VZ is equal to VL is equal to VI into RL by R plus RL. From the previous formula we find this, and if we solve this, then we can find RL is equal to R into VZ by VI minus VZ. So for this circuit, here it is given VI is equal to 50 volt, R is equal to 1 kilo ohm, and IR is moving through this resistance, IZ is through the VZ, that is 10 volt, and IZM is equal to 32 milliampere. And RL we have to determine the maximum and minimum RL, that is the range of RL. So for this we have to use the rule, that is RL, we see here RL is equal to R into VZ by VI minus VZ. So if we apply VZ, if we apply the values here, VZ is equal to 10 volt, 10 into R is equal to 1 kilo ohm, that is 10 cube, and by VI, that is 50 volt minus 10 volt. So we have found RL, the RL is 250 ohm, that is the minimum RL value. Now VR is 40 volt if we apply KVL, and RL will be, and we have also already said that RL will be maximum where IL is minimum. So if we want to identify the maximum region of RL, then we have to make IL minimum, and IL will be minimum when IZM is maximum, because we can apply the KCL rule here, that is IR is equal to IZM plus IL, and if we say IL minimum is equal to IR minus IZM, that is maximum Zener current. So it is 40 minus 32, that is 8 milliampere, and this is the lowest IL load current that flows through the RL, and so the R max will be 10 by 8, that is 1.25 kilo ohm. So we have found the maximum and minimum region of RL. The maximum value of RL is 1.25 kilo ohm, and the minimum value of RL is equal to 250 ohm. And by this we have also found that IL is equal to 8 milliampere, and if we apply the voltage rule, that is I is equal to V by R, then we can also find the maximum value of IL. So it is finished. Let's move to the another part, third part and the last part, that is Vi is variable but RL is fixed. For this we need to identify the range of Vi that makes the Zener to be on. So we have to find the minimum voltage and the maximum voltage. Vi, that is V minimum, is equal to VL into RL plus R by RL, and we have also found this by solving the previous equation, that is VL is equal to Vi into RL by R plus R, and by solving that equation we can also find the Vi. Next, the IZM, if we said if the maximum Z is given, then we can identify IZM, the Zener current, and IR max, that is. Let's move to the math. Here in this problem we have to find the range of Vi, so it is not given. R is 220 ohm, VZ is equal to 220 volt, VZ is equal to 20 volt, IZM is equal to 60 milliampere RL is equal to 1.2 kilo ohm. So V minimum is equal to 20 into 1.2 K plus 220 by 1.2 K from this rule. So V min is here, and IL will be 20 by 1.2, that is 16.67 milliampere, and from this we can also find IR max, that is 60 plus 16.67, that is 76.67 milliampere, and VIZ max, and the maximum range of VIZ max 76.67 into 0.22 K, that is 220 ohm plus 20 volt. If we apply KVL we can find this, and I hope you will also find this. You can also determine this by applying KVL, and by this we can find that the maximum or minimum range of voltage Vi, input voltage, and from this we can say that the Zener is on for which value, for which range of Vi, the input voltage, the Zener will be on. And by using these three math process we can use a Zener as a regulator. So thank you so much for watching my videos. If you have any suggestion, then please comment below, and please click the like button if you like it. Thank you very much.